This is Algebra 2, Unit 11, Lesson 8, on the frequency and period of a sinusoidal graph. Okay, so the final transformation will allow us to horizontally stretch and compress sinusoidal graphs. So we're thinking like squeezing them, basically, left to right. It is important to be able to do this, especially when modeling real-world phenomena, because both periodic functions do not have a period of 2 pi. The first exercise will illustrate the pattern. Okay, so let's take a look. On the grid below, this is the graph of the function y equals 3 cosine x. So we have changed the amplitude to be 3. So your amplitude from the midline, distance from the midline, is now going to be 3 from the cosine graph. Okay, so using your calculator, sketch the graph of y equals 3 cosine 2x. So I'm going to grab my calculator. All right, well, first of all, I'm going to put in 3 cosine x so that we have it. I'm going to put in the black one so it looks like it's on the paper. 3 cosine x. And then in the blue one, I'm going to put 3 cosine 2x. All right, so that's going to look like what's on the paper. 3 cos 2x. All right, I want to make sure I'm in radian mode. Right here's the radian mode. And to set my window, it's going from negative 2 pi to 2 pi again. So negative 2 pi to 2 pi. And my scale, again, is pi over 2. And my y's for this one is from negative 4 to positive 4 again. So let's use negative 4 to positive 4. So this will look like what's on the paper. Okay. Now, if I hit my graph key, all right, there's the blue one that we were just doing, and there's the original one that we have. Okay, so let's graph the blue one. All right, so the blue one, all right, so 3 cosine 2x in blue started here. It started in the same place. And then it goes down to here at negative 3. And then it goes back up to here. And then back down. And then back up. And then back down, and then back up, and then back down, and then back up. So it looks something like this. Oops. All right. So you'll notice it's still the cosine graph, except it's like been squeezed. If you went squeezed left to right like this, it kind of compressed it together. All right, so we have graphed here. This is the blue one is y equals 3 cosine 2x. So there's my graph. So how many full cycles or periods of this function now fit within 2 pi radians? All right, so here's from 0, here's to 2 pi. How many times did we do the full cycle of cosine? We now have 2 full cycles. All right, because remember the cosine graph goes like this. Well, we've done 2 full cycles of that from 0 to 2 pi. All right, now let's see what happens when we do 3 cosine 1/2 x. All right, I'm going to do that in red. So I'm going to do the red graph here, y equals 3 cosine 1/2 x. Okay, and let's see what that looks like. All right, so 3 cosine 1/2 x starts down here at negative 3, and then it goes, kind of continues up to here to 0. Let me do this in red. And the 0, and then it goes up to here, and then it comes down here, and then back down here. Okay, so how many full cycles of cosine do we have? All right, well, let's see. From 0 to 2 pi, usually we would go down and come up like that from 0 to 2 pi. But if we're starting from 0 to 2 pi, how much of the cycle do we actually have? We actually have half a cycle. All right, so instead of going a full cycle here, we're only going half of the cycle between 0 and 2 pi. Okay, so what we are just talking about is called the period of the function. All right, the period, or p, of a sinusoidal function is an important concept. It is defined as the minimum horizontal shift needed for the function to repeat its fundamental pattern. So we know for cosine, it should look like this over one complete pattern. And for sine, it looks like this for one complete pattern from 0 to 2 pi. So what we were looking at the period is how long it takes of the shift to repeat the pattern. So when is this pattern going to appear again? So the period for the basic sinusoidal graphs is 2 pi. So over 2 pi, cosine should look like this, sine should look like that. Clearly from our first exercise, the period of the function depends on the coefficient b in the general equation. So when you see y equals a sine b of x and a equals cosine b of x, the coefficient b is known as the frequency. All right, it's how many times it repeats the pattern over the period. All right, now remember back here, this was 2 for this one, and we had 2 complete cycles within 0 to 2 pi. For the red one, we had half a cycle. So if we think of that, it's telling you how many times the cycle repeats within from 0 to 2 pi. All right, so consider the graphs from exercise 1 and state the frequency and period. All right, so for 3 cosine x, all right, 3 cosine x, the b value right here, remember it's y equals a cosine b of x. The frequency will be 1, the period will be 2 pi. So one complete revolution would be from 0 to 2 pi. All right, now for 3 cosine 2x, that was the blue graph, the frequency from this one was 2. Now if we look at the period, how long did it take to get one complete revolution for cosine? So if I start here, when did I get back to back to starting again? Well, it got it at pi. It took from distance for pi, because we went like this, it looked like this, starting at 0, and it stopped at pi, and then it did another one to go to 2 pi. So the period on this one is only going to be pi. All right, now, y equals 3 cosine 1/2 x. The frequency we said for this one is going to be 1/2, because that's this value right here. Now the period for this one, when would I have to repeat the pattern? And so I'd have to go down. I've only got half the value here. How long is it going to take to go to the next, to get the end of the cosine graph? Well, it's going to go another 2 pi. So that means that your period is going to be actually 4 pi. You won't get a complete revolution for 3 cosine 1/2 x until you get to 4 pi. All right, so clearly we can see from the previous exercise that the frequency and period are inversely related, which means one increases while the other decreases and vice versa. So as the period goes up, the frequency decreases, and as the frequency increases, the period decreases. All right, so if we examine the results, what is true about the product of the period P and the frequency B? All right, well, let's see, write an equation for this relationship. If we take B and we multiply it by P, we should get 2 pi. All right, now if you look at your value right here, B times P equals 2 pi, if we look at our values, if I take 1 times 2 pi, I get 2 pi. I get 2 times pi, I get 2 pi. And 1/2 times 4 pi will equal 2 pi. All right, so B times P will equal 2 pi. Now we can actually use this to solve for any of the variables. We could also solve this for P. P would equal 2 pi over B, or B is equal to 2 pi over P. So if you remember B times P equals 2 pi, you can solve for any part of this. All right, so let's determine the period of each of the following sinusoidal functions. Express your answers in exact form. Okay, so we know that B times P is equal to 2 pi. All right, so what is B in this problem? Well, B will equal 4. All right, and we're looking for P, so it would be 4 times P is equal to 2 pi. So solve for P, so P is equal to 2 pi divided by 4, which is pi over 2. All right, y equals 8 cosine pi over 3x. Well, what's B? B will equal pi over 3. So let's see, B times P, pi over 3 times P is equal to 2 pi. All right, now, when we divide by pi over 3, we're really multiplying by the reciprocal. So we're going to multiply by 3 over pi. Multiply both sides by 3 over pi. All right, so these are going to cancel out, leaving just p. And 2 times 3 is 6. So p is going to equal 6. All right, and for this one, y equals negative 12 sine 2/3 x. B is going to equal 2/3. All right, so b, 2/3 times p is equal to equal to 2 pi. All right, multiply by the reciprocal is 3 over 2. So p will equal 3 pi. So basically what this means is if we were graphing this, p equals 3 pi, it would take 3 pi for the complete sine graph to happen. So it would take over a function of 3 pi. This one, it would take a period of 6 for it to repeat. This one would be a period of pi over 2. Okay. All right, so I think we're going to skip exercise 5. We're going to save that for class. Let's go right down to exercise 6 to finish this up. So the heights of the tides can be described using a sinusoidal model of the form y equals a cosine bx plus c. If high tides are separated by 24 hours, which of the following gives the frequency b of the curve? All right, now, in order to figure out b, we know b times p is equal to 24. Now, remember that the high tides are separated by 24 hours. So it means it's the distance from high tide to high tide is going to be 24 hours. So if I were to sketch this, it would be high tide 1 from here to here would take 24 hours. That would be the period. Okay, so if b times p is equal to 2 pi, not 24, I'm sorry, is equal to 2 pi. All right, if I wanted to find the frequency, which would be b, I have to know what the period was. So the period here is going to take 24 hours to get back to high tide. All right, so we'll go like that. So p is going to be 24. So 24 times b will equal 2 pi. So solving for b, divide by 24. b is equal to 2 pi over 24, which reduces to pi over 12. So it would take pi over, each of these would be divided into a section of pi over 12 in order for this to be to work. So the frequency of b would take pi over 12 to be 1 complete revolution. So that's going to be 3. Okay, so we'll finish up the rest of this in class the next day.